All right, so we have our change in energy of the system is equal to energy in minus energy out. The change in energy of our system, like we've seen from chapter 2, is our change in kinetic energy plus our change in potential energy plus our change in internal energy. These being total kinetic, total potential, total internal, they're including a mass term here. And then our energy in, the way that the book is writing this, typically what they do is our energy in is going to be heat coming in and then work going out. So for instance, if you are heating up water to create steam to create work. So here's really where this main equation is coming from. However, whatever term you have as your in term are going to be your positives, and whatever term you have as your out term are going to be your negatives. This makes sense because we do the same type of nomenclature. If you have Q coming out, this is what we call negative. If we have Q coming in, heat coming in, this is what we call positive. So when we're setting up a problem, if we know that there is work being coming into the system, we're going to actually have this work as an in term, a positive term. So for this setup of a problem, we have heat that we know is coming in, and we have work that we know is going out. But we can change what's coming in and what's coming out. So I'm going to do an example problem today and kind of try to illustrate this a little bit more. All right. So continuing, we're going to start looking at one of my favorite topics, specific heat. If you have my thermo class, you've probably already heard me talk about specific heat a good amount, but I really like specific heat. It allows us to live in the world we live in. And I think water is fascinating, and partially because of its specific heat. So specific heat, I've already defined this, I think in chapter 1 or 2 briefly, but specific heat is the energy required to raise the temperature of a unit mass of a substance by 1 degree. So it's an energy required to raise the temperature of a unit mass, the temp of a unit mass of a substance by 1 degree. So if you look at table A2 in the back of your book, why is it just a unit mass? Any reason? It's because this is a general definition that can be used in English or metric units. So it could be 1 pound, 1 gram, 1 whatever, but it's a set unit mass. And I'll go through that a little bit more in a second. But if you look at table A2 in the back of your book, it has these CP and CV values, which I'm going to talk about in a minute, but these are your specific heat values. If you look at table A3 in the back of your book, this has our specific heat values for liquids, solids, and foods. Table A2 is for gases. Sorry, I should have mentioned that. And you can see in table A3, it's interesting, they give the specific heat for things that are, normal things like wood and silver, but then they also give this specific heat for things like butter, ice cream, cheese, turkey, milk, and a lot of it's based on water content, but it's just kind of interesting. Like in your thermo book, you can get information about butter and shrimp. Okay, and then if you look at the very back cover, I haven't checked all the editions of the book, so I hope that this is right. The very back cover on the last row it has the units of specific heat. So like if you open the very back of your book, and then right here at the bottom of this page, it has like units of specific heat. So the units that we're typically going to be working with are kilojoule per kilogram degree Celsius. So energy per mass to raise by a given temperature. This is the same as kilojoule per kilogram Kelvin. We can use those interchangeably. And then this is also the same as 1 joule gram degree Celsius. So here's where that unit mass comes in, right? You can look at kilograms or grams. And then we also have some additional units such as 1 BTU per pound mass times degree Fahrenheit, which is going to be the same. We're also going to be able to use 1 BTU per pound mole Rankine. So I'm pretty much going to use these two, but just know that in the back of the book, you know, for any homework problems or any in-class activities, on an exam, I'm really going to only use likely these two. But all of these are in the back of the book on the back cover to discuss your specific heat. Okay. So using the chat from what you already know, and you probably, some of you have maybe heard me say it before, does water have a high or low specific heat? Water. Good quickness, Dan. Yeah, high. So water has a high specific heat. Does anybody remember its kilojoules per kilogram Kelvin or Celsius value? Yeah, 4.184. Yep, 4.18. Yeah, good job. So water has a high specific heat value. It requires a good amount of energy to raise a unit of it by a degree, which is why I went swimming at the beach this weekend and it wasn't burning hot, even though it was like 90 degrees outside, because water, it requires a lot of energy to change its temperature. It's why, you know, lakes don't freeze the second it gets cold outside. It's why the ocean doesn't freeze the second it gets cold outside. And it's just, it's fascinating. It has a really high specific heat, which allows it to resist a lot of temperature change and lets us live the way we live. Okay, so good job, everybody. Thanks for participating. I'm going to keep going. So when we're looking at specific heat, we have two types of specific heat. We have C sub V, which is our specific heat at a constant volume. Specific heat at constant volume. And then we have C sub P, which is specific heat at constant pressure. So as an example, using table A2, we can look up the specific heat for helium, a gas, and the specific heat at a constant volume for helium is going to be 3.12 kilojoules per kilogram degree Celsius. And the specific heat at a constant pressure is going to be 5.19 kilojoules per kilogram degree Celsius. So this is important for gases. They have different specific heats depending on if the volume is constant or the gas is constant. So you need to make sure you're looking up in table A2 either your C sub V or your C sub P based on your conditions. As a note, for incompressible fluids, or incompressible substances, let's say, for incompressible substances, which are liquids and solids. So gases are considered to be compressible, liquids and solids are considered to be incompressible. For incompressible substances, our specific volume at a or specific heat at a controlled pressure is going to be equal to our specific heat at a controlled volume. And so we drop this subscript and we just write it as specific heat, our term C. So this is relevant for gases, and for everything else, we don't care about volume or pressure. All right, so here's where you're going to use table A3 for solids and liquids. So table A2 is going to be for gases, table A3 is going to be for solids and liquids.
So I've got a quick question.
Yeah.
So when we're solving problems with specific heat, I was always kind of confused, but I think you just kind of cleared it up for me. I never knew when to convert my temperatures from Celsius to Kelvin, but I think you just said, like, apparently we don't have to. We can just use Celsius in the equations.
Yeah, so one thing that's like kind of remarkable about specific heat is this kilojoule per kilogram degree Celsius is completely interchangeable 1-to-1 with kilojoule per kilogram Kelvin. So if your answer or if your question is in Celsius, just use this unit. If it's in Kelvin, it's this unit. But it's going to be for water, it'll be always 4.184 kilojoules per kilogram degree Celsius or 4.184 kilojoules per kilogram Kelvin. So for specific heat, you don't really need to worry about the conversions.
Okay. Thank you.
Yeah. Other questions? Okay, great. So let's move on to how this relates to internal energy, enthalpy, and specific heat. And specific heat of ideal gases. Internal energy, enthalpy, and specific heat of ideal gases. So these have a relationship that we take advantage of a lot to solve problems. And one of the main relationships is this change in internal energy, du, is going to be equal to our specific heat at a constant volume at some given temperature times the change in temperature. And our change in enthalpy is going to be equal to our specific heat at a constant pressure for some given temperature times the change in temperature. So if we're to integrate this change in internal energy, and we're going to integrate from point 1 to point 2, or initial to final, whatever you would rather label it, and then from point 1 to point 2 of the other side of our equation, so I'm just doing an integration of our specific heat at a constant volume for some given temperature times the change in temperature. This equation gives us our internal energy at point 2 minus our internal energy at point 1 is equal to our specific heat at a constant volume average. This is going to be just an average term that we can pull out of the integral. This is what you're going to look up in your table. You don't actually have to include the average here. I'm just including it for clarity, and then times our change in temperature. So if it's easier for you to see, our change in internal energy is equal to our specific heat at a constant volume times our change in temperature. Doing the same thing for enthalpy from point 1 to point 2, our change in enthalpy, and then our integration from point 1 to point 2 of our specific heat at a constant volume at a given temperature and a change in temperature is going to be our enthalpy at point 2 minus our enthalpy at point 1 is equal to our specific heat at a constant pressure average times our temperature change. Or our change in enthalpy is going to be equal to our specific heat at a constant volume, constant pressure times our change in temperature. And these will have units of kilojoules per kilogram, just like we're expecting them to have. Or wait, actually, this is just kilojoules.
Sorry but so you just changed the units from kilojoules to kilogram
Yeah,
in the equation?
I couldn't hear that. Say that again.
Like I thought the equation was MC delta T, and then that would just give kilojoules. Or
Yeah, I got ahead of myself here. I'm working with specific volumes here, but I meant to be working with not specific. So I'm trying to figure out the best way to correct this. Let's just add per kilojoule here. And if these are specific, then that means we have to have a mass term.
okay.
But you could also do this as total the same way, and then just add your mass term later. I kind of combine both of them.
Okay.
So this could either be your change in total internal energy is this specific heat times your change in temperature, and the specific heat times your change in temperature. And then in order to make them specific, that's where you're adding this mass term. So these are your kilojoule, these are your kilojoule per kilogram. So here's this equation you've probably heard a bunch of times, like MC delta T. Will this be on our formula sheet? I haven't made the formula sheet yet, but yeah, probably. I mean, this part won't be. This part won't be, but MC delta T will be, I imagine. All right. So all right. I'm going to work an example problem where we're applying this equation. So for this example, a piston cylinder device initially contains a 0.5 cubic meter of nitrogen gas. A piston cylinder device initially contains 0.5 cubic meter of nitrogen gas at 400 kilopascal and 27 degrees Celsius. At 400 kilopascal and 27 degrees Celsius. An electric heater within the device is turned on. An electric heater within the device is turned on. and is allowed to pass a current of 2 amps for 5 minutes from a 120 volt source. Is turned on and is allowed to pass a current of 2 amps and for 5 minutes from a 120 volt source. Nitrogen expands at constant pressure and a heat loss of 2,800 joule occurs. Nitrogen is allowed to expand at constant pressure, or nitrogen is allowed to expand at constant pressure and a heat loss of 2,800 kilojoules occurs during the process. And a heat loss of 2,800 kilojoules occurs. Determine the final temperature of the nitrogen. Determine the final temperature of the nitrogen. A piston cylinder device initially contains 0.5 cubic meters of nitrogen gas at 400 kilopascal and 27 degrees Celsius. An electric water heater within the device is turned on and is allowed to pass a current of 2 amps for 5 minutes from a 120 volt source. Nitrogen is allowed to expand at constant pressure and a heat loss of 2,800 kilojoules occurs. Determine the final temperature of the nitrogen. Okay, so I learned this the hard way last year. Not all of you have taken physics 2, and many of you are not familiar with anything about electricity. So I'm going to tell you that electrical work is governed by this equation. Electrical work, work sub E, is our voltage times our current times our change in time. So this is your voltage. This is your current. And this is your change in time. So you don't really have to know anything about electrical work to solve this problem. You just need to know what this equation is. All right, so we have some sort of piston cylinder device. Here's our cylinder. Here's our piston inside the cylinder that is allowed to move up and down. We have an electric heater that is inside this device where we have 2 amps as our current and we have 120 volts as our voltage. And our change in time here is 5 minutes. We know that we have nitrogen gas, so N2. We know that pressure is constant. We know that our volume is 0.5 cubic meters. We know that our pressure is 400 kilopascal, constant. And we know that our initial temperature, T1, is 27 degrees Celsius. We know that heat is being lost from the piston cylinder, so we have a negative Q, and this is going to be negative 2,800 kilojoules that are coming out of our system. And we know that our work is positive because we have this electrical work coming into the system. So the book likes to kind of have a graphical representation of this system as well. So if we look at a pressure volume diagram for the system, at point 1, we're at 400 kilopascal, and at 0.5 cubic meters. We're told that the nitrogen is allowed to expand. So we have this piston that's coming up. So we know that we're going to have an expansion here. We're going to have some unknown larger volume, but we know at point 2, we're going to be at the same temperature. So our process diagram from point 1 to point 2 is going to look something like this. Okay. So we're asked to determine the final temperature of the nitrogen, which it's almost like, okay, well, where do you even like start? But oh no, sorry, hold on. My robot vacuum is gonna go and be very obnoxious. And my dog's sleeping, so we can't disturb him. Oh, thank you. I can stop there. Okay, so we know that in this chapter, the equation we've been working with is going to be this change in energy of the system is equal to energy in minus energy out. And we know that this is a gas. So that gives us a little more information. But in using this energy equation here to get started, we know that our change in energy of our system is going to be our change in kinetic energy plus our change in potential energy plus our change in internal energy. And this is going to be equal to our energy systems that are coming in, which is work in. And this work in is actually going to be our electrical work. And then what we have coming out, which is our heat minus our heat, which is our 2,800 kilojoules that are coming out. So this is work in minus heat out. Do we have any other work that's occurring?
Wouldn't that be work from the piston?
Yeah, exactly. So we've also spent a lot of this chapter looking at boundary work that's occurring when a piston is moving. We're told that this piston is allowed to expand, which means that there's boundary work being done out of the system. So we're going to have some negative boundary work that's occurring here as well. So we also have work that's coming out, which is our work out, which is our boundary work. Hold on, let me check something really quick. Okay. So we have our equation here. We know that we don't have any kinetic or potential energy because this is a stationary system. It's not moving. It's not on a roller coaster or falling down a turbine or anything. So our equation becomes our change in energy is equal to our work electrical minus our heat minus our boundary work. We're at a constant pressure. So our boundary work becomes the equation we've been working with all last week, which is our pressure times our change in volume, right? So our boundary work is here's the integration from point 1 to point 2 of our pressure times our change in volume, which just becomes our pressure times our volume at point 2 minus our volume at point 1, or our pressure times our change in volume at a constant pressure. All right, so we have our equation here, which is going to be our change in internal energy is equal to our electrical work minus our heat minus our pressure at point 1, our volume at point, those should be point 2. Don't write that yet. Pressure at point 2 minus our volume at point 2 minus our pressure at point 1, our volume at point 1. You don't need to write pressure at point 2, pressure at point 1 because it's the same pressure, but I think it makes it a little bit easier to see what I'm about to do. So I want you to recall the equation for enthalpy. So enthalpy is equal to what? Think about it for a second. See if you can recall it. So the equation for enthalpy that we went over at the beginning of last week is internal energy plus our pressure times our change in volume. So right now I can see that I have internal energy and our change in volume. So if I can recombine these, I can rearranging these pressure and volume terms to the other side. I have our internal energy at point 2 plus our pressure at point 2 times our volume at point 2 minus our internal energy at point 1 plus internal energy or plus pressure at point 1 times volume at point 1, Chokesha. And this is going to be equal to our electrical work minus our heat. So then this just becomes our enthalpy at point 2, and this can become our enthalpy at point 1. So our enthalpy at point 2 minus our enthalpy at point 1 is equal to our electrical work minus our heat. Oh, shoot. This part always confuses me. Ugh, I made a mistake. Not in this problem. I'll show you where I made a mistake. Okay, so all right. So in order for us to make this, sorry, I'm gonna change to a new page. Okay, so we're continuing this example problem. We have our enthalpy at point 2 minus our enthalpy at point 1 is equal to our electrical work minus our heat. And we can make the specific internal or our specific enthalpy pulling out a mass term. So our mass times our specific enthalpy at point 2 minus our specific enthalpy at point 1 is equal to our electrical work minus our heat. And then we know that our enthalpy at point 2 minus our enthalpy at point 1 is equal to our specific heat at a constant pressure, average, that we can look up in table A2, times our temperature 2 minus our temperature 1. So I made a mistake. This C term includes our mass term. So there is actually no mass out here. So the first thing I wrote was correct, and then I added that mass because I was like, no, there has to be a mass, but there's really not, because this includes our mass term. So we're gonna get to the MC delta T equation in a little while, but and the MC delta T equation is still correct, but it's not correct for these ideal gas equations. It's correct for your total heat change. So this always confuses me, and I apologize. So, okay, so now we can plug in our specific heat term for this change in enthalpy that occurs here. So this just becomes mCp T2 minus T1 is equal to electrical work minus our heat. So if we go to table A2 and we look up nitrogen, so you can see across the top it's labeled air, carbon dioxide, and carbon monoxide, whatever. And the fifth one, the second one in the second row is nitrogen in 2. And you can look at the temperature, which is given in degrees Kelvin. So our problem statement here is at 27 degrees Celsius. So we're going to go to table A2. And then we have 27 degrees Celsius plus 273 degrees Kelvin. And this is equal to 300. I should have done that in my head. 300 Kelvin. So now we can just go to 300 Kelvin over to nitrogen, and we can see that our CP, our specific volume at a constant pressure, which is what we want here, is 1.039 kilojoules per kilogram Kelvin. All right, so now we have CP. In the problem statement, we are not told a mass. So we don't have a mass. We do have CP. We're trying to find this temperature 2. We're told temperature 1. We don't know our electrical work, but we can calculate it, and we're told our heat. I thought M was in CP. Well, for this equation, it includes this per mass term. Okay, so the units here are kilojoules per kilogram, but it's because this CP has that mass term here. So the per unit mass is already in CP. But CP isn't mass, CP is specific heat. But it includes this per unit mass, which is why this is specific. Does that make sense? Okay. All right, so we want to try to figure out mass, and we need to figure out electrical work. So I'm going to target electrical work first because it's easier. So our equation for electrical work it was given to you, is our voltage times our current times our change in temperature. Our voltage is given in the problem statement as 120 volts. Oh, there's no line. It's just the volts. 120 volts. Our current is given as 2 amps. And our time is given as 5 minutes. We want to convert from 1 minute to 60 seconds. And we want to do this because there's a unit conversion which I would give you, but for this unit conversion, we have 1 kilojoule per second is equal to 1,000 volts times amps. So I don't expect you to know that conversion at all, but that's what it is. I would either give that to you in the problem statement, or I would probably not give you a problem with electrical work because we don't really do a ton of electrical stuff in this class. All right, so when we solve this out, we get 72 kilojoules as our electrical work. So now we have electrical work, and the only thing we're missing is mass. So how are we going to find mass when we have a gas that we don't really know about? This is volts times amps, VA, volts times amps. It's to cancel the units. All right, so when we're looking at a gas, for nitrogen gas, the first thing that comes to mind when you're thinking about a gas is the ideal gas law. So PV equals mRT. And therefore M equals PV RT. So we can find the mass for 0.1 by looking at pressure at 0.1, which we know because it's constant pressure, volume at 0.1, which we know since it's given, our temperature at 0.1, which is the temperature that's given, and then R is a value that we can look up from a table. Mass at 0.1 is going to be equal to mass of our whole system because this is a closed system. So we're able to use this equation to look at the mass of the whole system. So we're given our pressure of 400 kilopascal. Our volume is 0.5 cubic meters. Our temperature is 300 kilopascal. Nope, 300 Kelvin. 300 Kelvin. And then our R value, we're going to need to look up. So here's where we go to table, I believe it's A1, but yeah, so table A1. Right, good job, Layla. So table A1, and then we're going to look at nitrogen. And then you're going to look at the gas constant for nitrogen, which in my book looks like, so R for N2 is going to be 0.29, oops, that says 9, 0.297. 2968 kilojoule kilogram Kelvin. Brianna, why is it not 2.07? I'm not sure where you got that value from. Do you know, is that in your table A1? What edition of the book do you have? Yeah. Oh, okay. So, no, I'm just at table A1, not A1E, because we're looking in. Okay, that should still be fine because we're working in metric units. So if we go to table A1, and then we're looking at gas constant, and we're going to go all the way down to nitrogen down here. The value that I have is the 0.2968 kilojoule per kilogram Kelvin. Are your units the same? Is anybody else having an issue finding this? Oh, yeah. Oh, yeah. So this is nitrogen now. This isn't helium anymore. Okay. So 0.298 kilojoules per kilogram Kelvin. Remember the units for our value we can also use as kilopascal cubic meter over kilojoule Kelvin, which we're going to preferably use because of these kilopascal and cubic meters. So this R value is now 0.297 kilopascal cubic meter over kilogram Kelvin. And then when we solve this all out, I got the mass to be 2.25 kilograms. So now we also have this mass term. So now we can plug in to MCP T2 minus T1 is equal to our electrical work minus our heat. So this is going to be 2.25 kilograms times our CP value, which we looked up here, 1.039 kilojoules per kilogram. Let's do Celsius because we were given our problem in Celsius. And then times T2, which we're looking for, minus T1, which is 27 degrees Celsius. This is equal to our electrical work value, which is 72 kilojoules, minus our heat value, which is 2,800 kilojoules. And then we're going to rearrange and solve for this T2, and your T2 is going to be equal to roughly 57 degrees Celsius. I kind of rounded a lot because I was doing it on my phone, but about that, 56.8, 56 point, something like that.
So in the beginning, when we said that Q was negative 2,800 kilojoules, we're not saying it's electrical work minus Q, right? If that makes any sense, it's still minus 2,800.
Right. So that part gets like pretty confusing from the book, which is not ideal. So let me save this.
I don't know if what I just said made sense, but
No, it does for sure. But hold on, I want to. Okay. So for this problem, or for these problems, we're always starting with this energy, change in energy over system is equal to energy in minus energy out. So when we're first like drawing our system, so we have some sort of piston that's coming up. We know that this side is pretty much always for this chapter going to be our change in internal energy. This side is the side that we're concerned about. So instead of thinking about like negative positive here, it's easier to think about what's coming in. So for this problem, we know we have electrical work coming in through our heating device. So we have electrical work coming in. We have this piston is expanding. So we know that this is boundary work coming out. So we know that this boundary work is out, this electrical work is in. And then we're told that we're losing heat. So this Q is going to be out. So whenever we're writing this equation here, whatever is in is going to be our positives. And then whatever is out is going to be subtracted. If it helps you, you can also just look at like our system, right? So we have work coming, electrical work coming, or boundary work that's coming out. This is negative. We have electrical work that's going in. This is positive. And we have heat that's coming out. So this is negative. And you can just put these together. So boundary work is negative. Our electrical work is positive. Our heat is negative. But the way that I wrote it in the problem statement, I said, okay, this heat coming out is negative 200, negative 2,800 kilojoules. But I've already included this negative term here. So I don't need to do like negative 208, 2,800 kilojoules because I've like this negative term, these are coming from the exact same reasoning. So I don't need to include that again. So I really am just including like my negative work or my negative heat. Okay, I know my heat here is 2,800 kilojoules, and I just like essentially plug it in because at the beginning, I've already kind of worked out these negative and positives. Does that answer the question? Is that still kind of unclear?
I understand. Thank you.
Okay, yeah. Any other questions from anyone? You're not getting 57. So your math isn't working out that way. Are you, for the second temperature? Oh, it's because I don't have that. No, I don't. I think that I've been writing this as, okay, can you tell me in the problem statement, did I write 2,800 joules or 2,800 kilojoules? In the problem statement, I wrote 2,800 kilojoules. I wrote kilojoules. Okay, well then, yeah, that doesn't work out. It's supposed to be 2,800 joules. I hate not writing on the board. I hate writing on these things.
Wait, so are you saying that the initial problem statement should have been 2,800 joules, so that way when we did our math, it would have been like 2.8 kilojoules?
Right, exactly. Yeah. So this is problem 4.9 in the book. And I was just copying it directly. It says 2,800 joules, but I think I wrote 2,800 kilojoules. Yeah, in my work, I wrote all 2,800 joules. So this should definitely be joules.
I think you, because when I just asked you, you said it a different way. I think it's supposed to, you had it as kilojoules, and then when we work it, it goes to joules because then that makes it 2.8, or no, wait. Yeah, joules from the beginning, and then it's kilojoules in the work. Is that what you're saying?
Yeah, so when we have this initial piston problem here, and in the first problem statement, our heat leaving is joules. And then in the problem statement, a heat loss of 2,800 joules occurs during the process. Let me see if I can. Yeah. So in the in the problem statement, this 2800 kilojoules should actually be joules. And then that becomes 2.8 kilojoules. If you worked it with 2800 kilojoules, you're going to get like a huge negative value, which doesn't really make sense. So it should be 2800 joules. Okay. So your setup should be your electrical work minus your heat is equal to your MCP temperature 2 minus temperature 1. And your electrical work is 72 kilojoules. Your heat is 2.8 kilojoules. Your mass is 2.25 kilograms. Your CP is 1.039 kilojoules per kilogram Celsius, and then T2 minus 27 degrees Celsius. And so when you work out your T2, you should get about 57 degrees Celsius using this 2.8 kilojoules. So 2800 joules. This is example 4-9 in your book. So you could also, for example 4-9, what we did is we looked at using enthalpy because we could use this CP at constant pressure. We were told constant pressure. But you could also, here's the first way we worked it. You could also calculate boundary work, which is going to be your pressure times your change in volume, and then also look up your change in internal energy from property tables. You couldn't use your equation of your internal energy change is equal to your specific heat at a constant volume times your temperature change, because we aren't at a constant volume. So you have to look up your internal energy from your property tables. Okay. So I'm going to share this PowerPoint now. This PowerPoint's on your Canvas page. So we're looking at specific heat. This is your amount of energy required to raise the temperature of a unit mass of a substance by 1 degree. And then for gases, we're considering if it's at a constant pressure or a constant volume. For our gas, typically what we're doing is either trying to change this delta U term into MC delta T, or we're trying to change our delta H term into MC delta T. For gas, we need to consider if this is C sub V or C sub T. And here's an example problem you can work if you would like some additional practice. The answer is given here. And your C sub T is already given to you for those of you who have an international version of the textbook and don't have table A2E. I'm going to skip over that. We just did this similar example problem. Oh no, we just did this actual problem where we have our piston cylinder device that's being heated with an electric heater. We have boundary work, electrical work coming in, boundary work coming out. We're losing heat. Here's kind of just this problem we did, but this is condensed into showing you that we have our work minus heat minus work is change in internal energy. We converted this internal energy into change in enthalpy because that is where we can give work with our constant pressure specific heat. So here's the problem we just did, kind of displayed nicely from the book. And then this is the last problem that I'm going to do for the day. So we're cooling a piece of iron by putting it into water. So we have this 50 kilogram iron at 80 degrees Celsius that we are dropping into a tank to cool it. So am I able to? Okay. So we have this iron thing that we've put into a tank full of water. We're using an insulated tank, so there's going to be no heat exchanged with our tank being our system. So the reason that we have our delta Q is equal to 0 is because we are making our tank our system. So this is our system. And therefore, this insulated tank that's occurring means that our Q is 0. We also have no boundary work, no electrical work, no turbine work, no work at all being done. So we have our work is also equal to 0. Which means that our energy equation, our change in energy of our system, is equal to our energy in minus our energy out. We have no work, we have no heat. This whole side becomes 0. Our energy equation, change in energy of our system is going to be our change in kinetic energy, our change in potential energy, and our change in internal energy. This system is not moving. It's a stationary system. So our equation just becomes our change in internal energy is equal to 0. So here we can see worked out on this side, our change in energy of our system is equal to 0. And the change in energy of our system is going to be the change in internal energy of our water plus the change in internal energy of our iron. This is total change in internal energy. So here we're going to make this into M times our change in specific energy, internal energy, which is what gets us to this equation of our mass times our, this is a liquid and a solid, so it doesn't matter what sort of specific heat we have anymore, specific heat at a constant volume, specific heat at a constant pressure. For incompressible fluids, we don't care. So this is going to turn into our specific heat times our change in temperature for our iron plus our mass times our specific heat times our change in temperature for our water. And this is going to equal 0. All right, so coming back to this whiteboard to kind of work out the problem, we have our change in energy of our system is equal to 0. Our change in energy of our system is going to be equal to our change in internal energy of our iron plus our change in internal energy of our water. This is total change in internal energy. So if we make it specific, this could be our mass times our change in specific internal energy of our iron plus our mass times our change in specific internal energy of our water. We know that our specific heat term is going to be equal to our specific heat at a constant pressure times our specific heat at a constant volume, or these are all the same because we have an incompressible fluid. So we don't care what they are. So we're just using specific heat as M. So here we have our mass times our specific heat times our change in temperature for the iron, and our mass times our specific heat times our change in temperature for our water. We're going to go to table A3. In the book, and we can see for iron, our specific heat is 0.45 kilojoule per kilogram degree Celsius. And for water, we already know that this is 4.184 kilojoules per kilogram degree Celsius. We're told that our mass of iron, in the problem statement, or in the problem, like in that thing, is 50 kilograms, I believe. And that the mass of our water in this big tank is going to be 500 kilograms of water. And we know that our temperature initial of the iron is 80 degrees Celsius. We know that the temperature initial of the water is 25 degrees Celsius. And we want to determine the equilibrium temperature, which is temperature 2, of the iron and the water. They're going to come to equilibrium temperature. So this is going to be the same temperature. T2 of iron is going to be equal to T2 of water. So T2 iron equals T2 water here. So now we have the mass of our iron, our C for our specific heat for our iron, and we know our T1 for our iron. So we have like what we need from our delta T. We know the mass of our water, our specific heat of our water, and then we have what we need to solve for T2 of our water. So now we have everything we need to solve. We can just solve it. So for those of you taking notes, I would keep writing under this, but I don't want to clear all this because I have it here. So I'm just going to write to the side. So our mass of our iron is 50 kilojoules. Our specific heat of our iron is 0.45. Or the mass of our iron is 50 kilograms. The specific heat of our iron is 0.45 kilojoules per kilogram degrees Celsius. And then we have T2, which we're solving for, minus T1, which is 80 degrees Celsius, plus the mass of our water, which is 500 kilograms, times our specific heat of our water, which is 4.184 kilojoules per kilogram degrees Celsius. And then T2 minus 25 degrees Celsius. So it is important to note that this water specific heat is at 25 degrees Celsius, about average temperature. If we would have been at 0 degrees, we would have been at 4.22, which is really close anyway. If we would have been at 50 degrees, we would have still been at 4.18. If we would have been at 75 degrees, we would have been at 4.19. And if we would have been at 100 degrees, we would have been at 4.22 again. So pretty much we're always going to be at about 4.18, 4.19, 4.2. But this is the value for 25 degrees Celsius. So now we just want to solve for T2 for both of these equations. When we work out T2, we get our equilibrium temperature is 25 6 degrees Celsius is our equilibrium T2 for both the iron and water. For iron and water, this is considered to be our equilibrium temperature. All right, so it's 12:45, but the last thing I want to note is our iron went from 80 degrees down to 25.6 degrees, 25 degrees. And our water went from 25 degrees to 25.6 degrees. Right, so the amount that our water changed was 0.5 degrees, 0.6 degrees Celsius, and the amount that our iron changed was 54.4 degrees Celsius. So our iron cooled way off and our water barely heated up. And this is because water has a high specific heat. It's fantastic. All right, so reminder, there's no class on Wednesday. Homework is due on Friday. We'll do an in-person problem solving and online problem solving again on Friday. Your exam is next Friday. Please finish reading chapter 4. Please do the chapter 4 homework. And I will see you all on Friday unless there's any questions right now. You don't have to read the topic of special interest because it's not going to super help you on an exam, but it's about like dieting and calories in food, which is just kind of interesting. All right, with that, everybody have a good day. Where can I find the specific heat of water? It's in the tables in the back of the book. So it's in the same tables. So table A3 and table A3 has iron, but it also has water. So table A3 at the bottom, there's water. If you go all the way over to the end, here's your specific heat of water at different temperatures. Did you find it, Layla? Table A3 is what we use for all liquid, solids, and foods. Okay, well, everybody else, if you don't have any questions, have a good day. No class on Wednesday, so have a good middle of your week, and I will see you all on Friday for problem solving.
Bye, have a good day.
Bye, have a good day, everybody. You're good to leave. I'm gonna stay and help Layla make sure she can find it. Okay, so Layla, maybe can you turn on your screen or your camera so I can see like where you're looking? If you can't, that's okay. But what edition of the book do you have? Ninth edition. Okay. So I'm looking in the 8th edition. What page number are you on? So you should be on page 886, table A3. And then the very, very last row on page 886, it's the substance is water. And then if you go all the way to the very last column of liquid properties, you have specific heat, CP. It doesn't matter, it's just C. And then if you go all the way down and we're at 25 degrees Celsius, you have 4.18. Did you find it now? Okay, perfect, great. Glad you found it. All right, any other questions about anything? Yeah, there's so many tables, it's easy to look at the wrong one. Okay, great. Well, then have a good rest of your week. I will see you on